Okay, so for this experiment, this is called torque, specifically torque and equilibrium. Equilibrium is going to be a point that we get to as it relates to torque. And so you'll see in just a second how those two are going to be related. So on the left side is the document that you will be using. On the right side is the simulation. I'm actually going to go to the simulation that is titled Balancing Act, or Balance Lab, and it gives us a few more tools to work with. All right, just so you're clear on what this table is saying. So you're gonna have 4 trials to look at, and in each trial, you're gonna be given either one side or 2 sides of this seesaw fulcrum piece that you're going to be trying to balance out. And so, for example, in trial 1, you're going to take a 10 kilogram mass and place it at the 1 meter mark. So what this means here, just for clarity, is that the position of the column, this is the position of the column to the left. So what I'm saying is this value refers to this, this column. For example, this column here, which has 3 objects here, this object refers to those 3 those 3 objects. So we're going to place for trial 1, you're going to place a 10 kilogram mass at the 1 meter mark. And the easy answer, obviously, is to put another 1 or 10 kilogram mass at the 1 meter mark. And so, I mean, that's an easy answer, but you probably want to challenge yourself and ask yourself, well, what can I balance this out with a 5 kilogram mass? Can I place it here? Well, obviously, I probably can't place it here, but can I place it here to balance it out? And yes. And so what we've done is we've created torques in 2 different directions. Torques are basically a rotational force. So we've created 2 torques that balance each other out, that counter one another. So there's multiple answers that I can get the torques to balance out. Okay. So you're going to work in that area. And this is a pretty short, a short experiment, but it's just going to have you kind of look at how torque and equilibrium, how to work with that. And so also what you're going to want to look at, let's give you a kind of a more in-depth review on what we're looking at here. You're probably going to go over this in your lecture as well. And so basically, again, what we have is we have some maybe a plank of some kind and a fulcrum point here. So this emulates the seesaw. And we would take an object. In this case, I have the object that has a mass of 10 kilograms. And if I multiply it by the acceleration due to gravity, the units turn out to be newtons. So I get 98 newtons. So this force here, this purple force, is the magnitude of the force and the direction of the force, straight down. This dotted line here is called the line of action of that force, which we call W. And so to look at this a little bit more in detail, we use the Greek letter tau for torque. Our perpendicular is this arm lever here. You probably can't see it, but it has an arm length of 1 meter. And we would multiply by the force. The force in this situation is just basically W. So you can replace that. And when you do the math here, you'll see that the torque is 1 meter times the 98 newtons. So you would get 98 Newton meters for the units and the torque associated with this. So typically for torque, you were, if you were to calculate this, to distinguish it from work, because if you remember, work is also measured in Newton meters. Some books you'll see that it's in terms of a meter Newton, so they kind of flip flop. Not all books, but some books. So in order to get this balance, we could, at this point here, in reality, the seesaw would not be in balance, so it would kind of do this, right? Because there's, obviously there's a mass on that side, right? So the true position probably looks more like this. So I just kind of want to introduce you to some new terms here. Line of action, you're going to see that in your lecture. Greek letter tau, which is used for torque, and R perpendicular, which is basically a straight line from some reference point to the force or line of action of the force. And so you can, see if I can get this out of the way. You might also see a different format for torque, which uses either sines or cosines in order to get your answer for the torque. So just be mindful that for most of these cases, you want this to be, in some of these cases, you're going to want these to be in equilibrium. And so you're going to want that counter torque over here to balance such that the sum of all the torques, let's see if I can write this down. So the sum, a little bit messy, sum of all torques tau equals 0. Sum of all forces in the x direction equals 0. And the sum of all forces in the y direction equals 0. When all three of these are met, this implies that you are in equilibrium. Okay. All right, good luck.